Hello everybody. Welcome to When T-Tests Go Bad, Assumptions of the T-Test and the Log Transformation. This is Elizabeth A. Albright of the Nicholas School of the Environment. Thank you for joining in. So what do we assume when we use a two-independent sample t-test? First, we assume that populations are normally distributed. Again, we make assumptions about the populations, not the samples. We test our assumptions with the samples. And we also assume independence of observations between and within groups. So this is typically a function of the sampling process, random sampling, experimental design, data collection, and the data themselves. So asking questions about, is there spatial or temporal autocorrelation? Are observations that were collected close together in space more related than observations that are further apart in space? That's what we mean by spatial autocorrelation, or temporal, same thing, but with time. So things we need to think about as we proceed. So the two independent sample comparison of means test, or the Welch's test, we do not need to assume equal variance of the two populations, right? And we will use this t statistic, the x bar A minus x bar B minus mu A minus mu B. Typically that mu A minus mu B is set to 0 if we are hypothesizing in our null that there is no difference between the two populations, no difference between the means. And that's all over the square root of s sub a squared over n sub a plus s squared sub b over n sub b. So what happens to our results when the t-test assumptions are violated? And we're going to really focus on that normality assumption today. We'll get into autocorrelation, spatial temporal issues later in the semester. So one, the confidence intervals may be incorrect. Right? We can run simulations to see, run 1,000 or more confidence intervals pulled from populations, see how many of the intervals cover the true difference in population means. And if we're not meeting the normality assumption, that we may not be getting, say if it's a 95% confidence interval, we may not be getting 95% of the confidence intervals covering the true difference in population means. So what does that mean? We may find an effect is significant when it's not, or vice versa. It's problematic. We may report erroneous results. So when does this happen? When does a t-test do a bad job? One, with highly skewed distributions, especially if the shapes of the two distributions are different. When there are outliers, t-test is not robust to outliers. And when our sample size is small, and that really stems from the central limit theorem. I recommend watching the central limit theorem video once that's up. Central limit theorem saves us when n is large. This question about what is small, it really depends on what those distributions look like. Moore and McCabe, kind of a standard stats 101 book, says small is less than 40. That's again a rule of thumb. It really depends on what the distributions look like. So is a t-test a good test? It's generally robust, right? Even if assumptions are violated. And we should know that the two sample t-test is more robust than a one sample because we're looking at the difference in means versus one mean. So something to keep in mind. But skewness can cause problems. So we need to look for skewness and deal with skewness if necessary. Which gets us to our example today. And we're going to think about and examine air quality across states. Just looking at two states because we're doing a two sample independent test, two independent sample tests, at one point in time. And I decided to look at Arizona and California, and we will be examining ozone layers, ozone levels. So our question is, does California or Arizona have higher ground level ozone levels on July 1. Did they have higher ground level ozone levels on July 1? There's our ozone molecule that will be with us today. So we set up, first thing always, a priori, set up our hypotheses. I am not presupposing that Arizona's ozone will be higher than California, so I'm going to do a two-sided test. So our null is that the mean ozone in Arizona minus mean ozone in California is equal to 0. And the alternative is that the mu ozone in Arizona minus mu ozone in California is not equal to 0. So a two-sided test. And here's our data. I sourced it from the USEPA and imported the data and called it airquality.df, just short for data frame. For those of you that are using R, I will introduce a little bit of R in the video, but then we'll make the data and the code available. So here is the data frame, or the data set. As you can see, we have about 7 variables. State name we'll be interested in, and forgot to turn off my email when filming, so excuse the beeps. Date local, and we are measuring ozone in parts per million. It's ozone collected over an 8-hour period. So data. So now we need to make our data frame for analysis. This is what we call data wrangling, right? Management of data, getting it in the right form. So one of the things we need to do is tell R to recognize the date as a date. And so we can use the function as.date, put in the object, and tell it the format that it's currently in, so month, date, year. And then we can use the dplyr package to wrangle the data. And we're going to make a new data frame called ozone. And starting with the airquality.df, we'll pipe that to a filter where state name equals Arizona, or state name equals California. And then we pipe that to another filter to filter on the date. So date.local equals parentheses 2019-07-01. So we are only interested in the air quality on July 1st in Arizona and California. And now, once we have our new data frame, ozone.df, we can run the t-test. So, does California or Arizona have higher ground level ozone levels on July 1? Probably should be past tense, but we'll just say July 1 for now. So, measured ozone at air quality stations across the states, the 2 states on July 1, 2019. The units are parts per million measured over 8 hours. And we find the summary statistics I calculated in the blue table, and that mean ozone in Arizona is about 0.0028 part per million, less than that in California. Right? Just subtracted those two means. As always, we make histograms or box plots to look at the data. So I used a facet function, I guess, design perhaps, to display the data here. So we have Arizona in blue up above and California in gray down below. And I can share this code with you as well. It's nice. You can see how they align. The Arizona distribution doesn't look as skewed as the California distribution. California distribution looks more positively skewed. So a good way to compare distributions across groups. So let's ignore the distributions at this point, what they look like, and go ahead and run the t-test. Let's run it. Although this might be problematic, right? We know that's problematic. We talked about that. But let's go ahead and run it and see what happens. So our code, t-test, ozone, it's a function of state.name. State.name is that grouping variable. It's either going to be California or Arizona. And then ozone.df, that is our data frame. Ozone is the vector with the ozone data in it. Then we have state name, and that's our grouping variable, data frame, t-test. And we get our results. The Welch two-sample t-test. We get a t of negative 2.4664. I ask you, why is that negative? Right, because we're calculating Arizona minus California. That's how R is reading it. Calculates the degrees of freedom and gives us a p-value of 0.01449. The alternative hypothesis is the true difference in means is not equal to 0. That's a two-sided test. P-value, we reject the null, and we have evidence to suggest that there is a difference in means in the true difference in means excuse me, in the populations. But we really need to think about the assumptions, right? We can't just report the t, the degrees of freedom, and the p-value and call it a day, right? We need to think about those assumptions and see whether or not these results are valid. So it could be problematic based on our histograms. One thing that I do sometimes is run a test for normality. That's a test that to see whether the samples were pulled from normally distributed populations, sample or samples, in this case, two samples. So the sample was pulled from a normally distributed population. So in this case, just for simplicity, we could have done it a little more quickly, but I made two new data frames, an Arizona data frame and a California data frame, again using the pipe. So Arizona.data frame, I'm assigning that the ozone.data frame piped, so carrying through, and now we're going to filter state name equals Arizona. Same thing with California. And what are our results? You should know that the Shapiro Wilk test, the R code is shapiro.test. The null is the sample was pulled from a normally distributed population. Right? So we do not want to reject the null if we are to uphold the assumptions. So it looks like we have a p-value of the Shapiro Wilk normality test 0.2112. We don't reject the null. All right, that one looks okay, which makes sense if we think back to the histogram of Arizona. It looked more normally distributed than California. Then I run the Shapiro Wilk on California, and we get a p-value, tiny p-value, and that just screams problematic to me. So is our normality assumption met? Likely not, right? And we have different skewness, or different amount of skewness in our two distributions. Our sample size is not great. I'm not totally convinced that we should stick with just running the t-test on non-transformed data. So how could we fix it? Where do we go from here? Do we throw in the towel and go home, call it a day? Maybe, maybe not. No, right? We've got a solution, or at least a couple of different approaches we can take. And today I'm going to talk about the log transformation. It's a common transformation we can do to then prepare the data to run the t-test on log transform data. So the logarithm, just a quick review. Log base 10, 10 squared equals 100. Log base 10 of 100 equals 2. Right, so that's where the 10 goes, that's the 2, and that's the 100, right? That's the essence of a logarithm. Typically, or oftentimes, we don't use log base 10, but we use other logs, or the natural log. And what is log a shorthand for? It's what power should I raise the base to in order to get x. So what power should I raise the base to in order to get x? So we typically use the natural log. Not always, sometimes we use log 10, but and in R, that is the function log parentheses. Oftentimes outside of R, it's signified by ln, or natural log. And here, this is a photo credit I'll give to Ramsey and Schaefer, Statistical Sleuth. I love that book. If you haven't looked at it, the chapter. It's awesome. So here we have the data. If you look at the horizontal line through the middle of the figure and the distributions that are dropped below it. So before, both histograms are skewed. The one with the larger center also has the larger spread. All right, so then we log transform it and look at the distributions now along the y, and there's no skew and they have roughly the same spread, right? So what this does, oftentimes it doesn't fix everything, but it's a useful tool to use or try. And that's the logarithmic transformation used to arrive at favorable conditions for the two-sample t analysis. So we know that skewness can be problematic for t-tests. So let's apply the log to our data and see what the distributions look like. Let's see if that skewness through the use of the log distribution became less problematic. And we can make this new variable ozone.df, so we're putting it in our data frame, a new vector called log.ozone, and assigning it the value of log of ozone.df ozone. Right? So we are making a new vector and assigning it to the log values. And here we go. Wow, they look better. The Arizona distribution didn't shift a whole lot, right? But the California one did. It looks less skewed. And as you can see, the units on the x-axis shifted. We're now talking about log parts per million, and the values shifted. So I'm feeling a little better. I'm feeling that this may be a good approach. We can run the Welch's t-test on the log data. So now we need to make assumptions about the log ozone in the populations, not the ozone. And I'm much more comfortable making assumptions about the population of the logs than I am the original data based on the samples. Again, we make assumptions about the populations, not the samples, but we test our assumptions with the samples. So here's our results. I ran the t-test again, the Welch's t-test. T equals negative 0.99148. Again, this is on the logged data. Degrees of freedom shifted a little bit because the standard deviation shifted, and we have a new p-value. If you remember before, our p-value was pretty tiny, and now our p-value is not. It's 0.3227. Again, our alternative hypothesis is true difference in means is not equal to 0. R also kicks out the 95% confidence intervals. And the mean in group of Arizona and the mean in group of California, we should know that those are the means of the logs. So what do we do? What do we do next? We need to interpret the log transform results for the two-sample test. We're not done yet. Getting closer. So hang on. But we need to undo the log, or take the exponential of the difference of means. So if we say Z1 is the mean of the log data of sample 1, Z2 is the mean of the log data in sample 2, we take Z1 minus Z2 and take E to that value. And this gives us the multiplicative factor of the medians. And this is because of our log rules. I encourage you to check out the log rule page on the statistics review site if you have are uncomfortable with the log rules and why a subtraction gives us kind of a multiplicative factor. So the t-test results itself, the t-stat, the p-value, the degrees of freedom, can be interpreted the same way. But we should officially talk about medians and not means. And this has to do with the logging and then back transforming. Right? So even if we make hypotheses about the means, which we did, the population means, we really now need to be thinking more about the central tendency of the medians. And this gets back to the log of the means is different from the mean of the logs, and I won't derive any of that, but just know that we should really be talking about the medians now. So our question is average is average ground level ozone levels higher in Arizona and California? We ran a 2 independent sample t-test. It was a 2-sided test. And here is what we do is we back transform the difference in means of the logged samples. So exp negative 3.336, I just took this from the R output, minus a negative, and that's the mean of the logged data. The first number is for Arizona minus California, and we get a value of 0.97. So what does that mean, that 0.97? That is the multiplicative factor. So we estimate that the median ozone level in Arizona to be about 97% of the median ozone level in California. This is on July 1st, right? There is not conclusive evidence to suggest that ozone levels are different across the two states. And we give our T, our degrees of freedom, and our p-value. We don't need to change those, exponentiate those, or do anything with those. We report the T, degrees of freedom, and p-value on the log data. But what we need to calculate is this multiplicative factor, because working with the log data, and it's good to kind of try to think about it in terms of the original scale. So now we need to talk about medians and multiplicative factors. So we estimate that the median ozone level in Arizona to be about 97% of the median ozone level in California. That's from that equation up above, subtracting the mean of the logged data of California from the mean of the logged data of Arizona, exponentiating that, and we get 0.97. So we have conflicting results, right? We found a very small p-value, highly suggestive when we ran the t-test on the original data. But then we logged the data and got different results. We didn't find a difference. Which one do I trust? What do we think is more valid? So meeting the assumptions of the t-tests are more critical when sample sizes are small, when skewness differs, normality assumptions not met, right? And so I would probably, if I were a betting person, put more weight on the analysis using the logged data than the original data. Ideally, I would go back, collect more data, right, which we have. I'm just keeping it simple using one day because we're doing a t-test, and if we use multiple days, then there's temporal autocorrelation, and we really need to think of this data as time series. But I took a slice of it, so we could use a t-test without really getting into the temporal autocorrelation issues. However, there may also be spatial autocorrelation, right? So ozone may be higher in, say, Los Angeles or in Phoenix, and if there are multiple stations located next to each other, we really need to question our independence assumption, right? So again, this may not be ideal to run a t-test on this type of data. It's good to think about these limitations as we move forward in this semester. We don't typically live in the world of t-tests. It is limited because of these issues. But this was hopefully an illustrative example to show when log transformation may help us reach more valid results. So, I've talked a lot tonight, and now it is your turn. So, what I would like you to do, and I will not read this to you, is stop the video, or as I like to call it, the movie, and read this problem, and please go ahead and solve it. And so I'm going to go to the next slide, and then I will go back to this slide, and the next slide tells you what you should be solving for. So what I want you to do is write and clearly label appropriate hypotheses for the analysis. Describe what kind of comparison test you should conduct. 2, discuss the assumptions underlying the test you selected in Part A. Be sure to discuss the assumptions in the context of the question posed. And 3, carry out your comparison test. Interpret your results with respect to the question posed in the prompt. Do plants grown with the new organic fertilizer yield more kilograms of tomatoes, and if so, by how much? So you might want to take a screenshot there. That's what you're answering. And then now I will go back to the problem. Feel free to stop the video. And I will post the answers early in the next few days. So thank you very much for joining in. I hope this video was helpful in terms of the 2 independent sample t-tests, the Welch's test, and the assumptions that underlie it, its sensitivities, and a way around it with the log transformation. The next thing we'll think about in class is non-parametric tests, where we don't make assumptions about the parameters of such as a normality assumption. So yeah, until then, have a wonderful day. Thank you again. I'm Elizabeth Albright, and thank you for listening. Bye-bye.